Yeah, I'm going to talk about some fairly simple work, which is a lower bound on leakage-resilient secret sharing with Jesper Boos-Nielsen, who's also at Aarhus University. And like, I assume everybody knows what secret sharing is. So like in this talk, we focus on threshold secret sharing. So we only care about like if the set of parties is large enough, they can reconstruct the secret. If this set of parties is, so I secret share a file. If the set of parties is large enough, I can reconstruct the secret. If the set of parties is too small, then I cannot reconstruct the secret, and it's, let's say, perfectly hidden. And very recently, there have been a lot of talks that consider notions which are kind of very different in the flavor of secret sharing than all of the previous ones. So all the previous notions like secret sharing, verifiable secret sharing, robust secret sharing, they all considered kind of like a binary adversary in the sense that an adversary had kind of either full access to a share or no access at all. So like be it passive or active access, but like some shares were completely hidden and some shares were completely revealed to the adversary. And since basically last year, there was a huge explosion in papers who all decided to work on the same problem at the same time, which is great if you also work on that. So there are basically two notions, and the idea is that what happens if we consider passive and active adversaries that have some form of access to all of the shares, okay? So, and then the first flavor of those is kind of a passive adversary where they consider leakage-resilient secret sharing, where we say, okay, let's say we have a secret sharing or like two different files that are secret shared, and then I obtain some leakage from every share of the existing shares. And if a secret sharing is leakage resilient, then basically we would like that the distributions of those leakage vectors are close to each other, okay? So usually like what we will consider throughout the talk here is basically that you can apply an arbitrary function to each share, and these functions have to be chosen kind of independently before you see any of those shares. And they're only bounded in the length of the output, okay? So each of those leakage function outputs some L-bit leakage. And then no matter which file with secret shares, the two distributions of those share vectors should be close to each other, okay? So this corresponds to kind of a passive adversary. And then there is also another notion which corresponds to an active adversary, where we say, okay, I secret share a file, and then an adversary specifies a vector of tampering functions. Each tampering function is applied to one of the shares. And when I reconstruct the secret, then I would like to have the case that either the secret is the same as it was before, or it is completely unrelated. Okay, so this is basically kind of the analogs of like non-malleable codes for secret sharing. Okay, and there are lots of works that basically aim to construct leakage-resilient secret sharing and non-malleable secret sharing in an efficient way for kind of different notions of what efficient means and different notions of what secure means. And an interesting other work in this area is basically from last year's crypto by Benamuda, Dekwika, Ishai, and Rabin. And there they ask a very interesting question. So when we try to construct all of those kind of primitives with these extra fancy properties, is there any chance that maybe like Shamir secret sharing already has those properties and we don't need to do anything? And what they basically show is that it is indeed the case that if you look at, does everybody know what Shamir secret sharing is? Okay, yeah. So, so if you look at Shamir secret sharing with a large enough threshold, then it is indeed leakage resilient. Okay, so like I'll gloss over what exactly leakage resilient here means, like what the parameters are, but like it provides some good leakage resilience for like some relatively large amounts of leakage. Yeah, so I think like a quarter, at least. So in the crypto version, it was basically t was n minus log n, and there it was roughly a quarter that you could leak from each share. And here,
this is with 1 bit, but it's a smaller constant.
Yeah. Okay. So with 1 bit, so 1 bit leakage here. Yeah. So basically, they showed okay for if we have a very large reconstruction threshold, or like reasonably large reconstruction threshold, then we do indeed get some leakage resilience automatically. And in their paper, they then conjectured, okay, maybe it is the case that actually for any constant c, if I have a c, so for any constant c smaller than 1, obviously, that if I have a c out of n Shamir secret sharing, that this gives me 1 bit of leakage resilience. Okay, so this is kind of the question. And basically what Jesper and I did is we said, okay, can we maybe in general find kind of some necessary conditions or like an inherent price that we have to pay if we want to construct any kind of leakage-resilient secret sharing? And can we then maybe use this bound to say something about Shamir's secret sharing? Okay. So one of the questions is like, so why do we focus on leakage-resilient secret sharing and non-malleable secret sharing? I won't kind of go into the details, but basically you can, in a straightforward way, you can show that if you have a secret sharing scheme that is non-malleable, then the secret sharing scheme is also leakage resilient. Okay? So if you then go on and say there is an inherent price to pay for leakage resilience, then this price also has to be paid for non-malleable secret sharing. Okay? To just kind of very roughly sketch why non-malleability implies leakage resilience is, so assume you have a secret sharing scheme that is not leakage resilient, okay? Then you know that there are two files and some leakage functions such that kind of the statistical distance between those two leakage vectors is large. So if the statistical distance is large, then there is basically a specific leakage output for which one of the files, one of the secrets is much more likely than the other one. And from this, you then just construct an adversary for the tempering, like a tempering adversary for the non-malleable secret sharing scheme by saying that if the leakage is exactly this leakage vector, then kind of it destroys the file at the secret. And if it's not the case, then it leaves it unchanged. Okay? And in this case, what you manage to do is you constructed a tempering adversary who manages to change the value of the secret shared file based on the secret, so to speak. And this is exactly what the non-malleable secret sharing wants to prevent. Okay? So in this case, you don't change it to like +1 of the secret, but you say, okay, like you destroy the secret sharing based on the secret shared value. And this already kind of is enough to break the security properties of non-malleable secret sharing. Okay? So that's why we focus on leakage-resilient secret sharing.
But the tempering is global right now, right?
So maybe I should specify. So both leakage and tempering here I consider is you specify a vector of functions and they are independently applied to each share. Okay, so every tempering functions if you have n shares, you specify a vector of n functions and each of those functions is applied to one share. Okay? So it's non-adaptive.
But in the reduction that you described from leakage-resilient to tempering, it seems that
I see. Yeah, so you don't need to have it global because you just if you know that it's not leakage resilient, you know that there is this vector. So like the first tempering functions will have L1 hard-coded, and then it will simply like apply the leakage function on the first share. It will check whether the bit is the same that I hard-coded. If it is the case, it does, which way around did we do it here? Yeah, so if it is the same, then it does nothing. And if it's different, then it will destroy the share. Okay? So then if you have a minimal access structure, so imagine you match.
So I don't understand. So when I get to L3, how do I know that L1 places L3?
You don't, but in the end, like, you know that if the leakage globally matched the leakage vector that you hard-coded in every function separately, you know nothing happened. You didn't change any separate specific share, right? But if one of those leakages didn't match if globally the vector doesn't match the vector that you hard-coded, then there is one index where you change it. Okay?
Maybe the reconstruction will still be the same, no?
So I'm glossing over some details. Basically, you consider a minimal reconstruction set. So if you destroy one of the shares, then you cannot possibly reconstruct. Okay, so that's why if you locally kind of see the leakage doesn't match, you destroy one share, and then you consider like a minimal reconstruction set where you're like missing one share, you have an unqualified set, so you cannot possibly reconstruct.
This is only for perfect, right? This is only for perfect.
Yeah. Throughout the talk, I just assume perfect security.
It doesn't seem to hold at least that. For statistical.
No, I mean, I just sketched it for perfect. Yeah. Okay.
Much more likely. So even if the distance is like 1/2, you would still have like the leakage would be any particular leakage would be exponentially unlikely, right? So take the example.
So if
X is 0, X is 1.
so basically, if you have, can I write on this? Yeah, I assume. So basically, if you have a non-malleable, so how do I explain it in the simplest way? So when you argue about non-malleable secret sharing, then you define a tampering experiment and you say, independent of which secret it is, the distribution of the outputs of this tampering experiment, they're close to each other, okay? And this closeness you define by a parameter. And if you then basically have a non-malleable secret sharing scheme which gives you, so let's say from each share, you leak L bits. Okay, if you want, like for a leakage-resilient secret sharing scheme. Okay? Yeah?
Like the loss is exponentially in and out.
Yeah. But if you then define the indistinguishability, like negligible in the security, like it is exponential in this, yes. But not in the security parameter, which you could then define, yes. Like you have a large loss, and I don't think you can get around this, but like this loss is, let's say, not too large. But like you lose a lot, like you don't get good leakage resilience from that. Yes. Yeah, sorry for being so hand-wavy, I just wanted to sketch it. Yeah.
Essentially, you're saying non-malleable code is not a good way to beat leakage-resilience schemes, because you're saying non-malleability implies leakage-resilience, right?
Yeah, I mean, like, it implies some leakage resilience. Like, if you want leakage resilience, that's not the way you should do it. But like, by default, if you have non-malleability, you also get some leakage resilience, okay? So like the leakage resilience that you get in terms of concrete parameters is not good. Like, but it does give you some leakage resilience, okay? Which is kind of important because if I then give you a lower bound on any leakage resilient secret sharing scheme, if you have some leakage resilient, automatically have some leakage resilience in the non-malleable code, this lower bound also applies to the non-malleable secret sharing scheme. So does this make sense? Okay. Okay, so before kind of going into the lower bound, let's just define some parameters. So we have basically n is the number of parties. T is the number of parties that are enough to reconstruct the secret. We say large L is the number of bits that I leak from each share. So in total, the leakage is n times L. Okay? And each share has a share size of p bits. And we'll define a very, very crude measure of randomness that just says if I have capital T shares, then this defines the full vector of shares. Okay? So small t says if I have small t shares, then this uniquely defines the secret. Capital T says if I have capital T shares, this defines all of the shares of this specific secret sharing. Okay? So you can, this is not a great measure of randomness, but for for illustrating here, it's good enough. So intuitively, it gives you kind of some notion of randomness in a secret sharing scheme that we will then use in the bound. Okay?
And you don't care about complexity, right? Like,
No, yeah, we care about information theoretic security, so the adversary can run in exponential time. Yes. Okay. So the lower bound statement is basically what we get is that if you consider a small reconstruction threshold T, let's say some constant reconstruction threshold, then either the share size has to be large or you have to have a lot of randomness across all of the shares, meaning that even if you have enough shares to reconstruct the secret, the remaining shares that you don't know still have to be containing a lot of randomness that is completely unknown to you. Okay? So basically, yes, if you say, let's say you have 1 bit, yeah, so this is basically what I said. If you have like a constant reconstruction threshold, either the shares are large or the amount of randomness across all shares is large. And using this bound, we can then also show that, sorry, did some slides go missing? No. Yeah, okay, sorry. There was so much discussion, I imagined that I didn't actually talk about this. Yeah, so in terms of the conjecture from last year's crypto paper, we can then use this simple lower bound to basically say that we still don't know whether like a constant fraction of n players as the reconstruction threshold provides you leakage resilience, but we can say that C times n divided by log n is not 1-bit leakage resilient for large enough values of n. Okay? So this kind of at least gives an indication that the conjecture that was in last year's paper is the best one can hope for in terms of leakage resilience from Shamir's secret sharing scheme. Okay? Yeah, so the proof works in a very simple way. And because we are proving a lower bound, we consider an even weaker notion of leakage resilience, because if we can show that an even weaker notion of leakage resilience has some inherent cost, then this cost is also inherent to any stronger notion of leakage resilience, okay? So the definition that I showed before was an indistinguishability-based one where I have a secret sharing of one of two secrets. Here we only consider a notion where we say, okay, you're given the leakage from a secret sharing, and the adversary then basically has to recover the file from the leakage that it sees, okay?
So it's a random file?
Yeah, you just quantify over all files, yes. Okay, so this is a weaker notion, so if we prove a lower bound for this, we have a lower bound for the other one as well. And the idea is simply to define some leakage functions and an adversary that kind of does something with the output of those leakage functions such that whenever the lower bound is violated, the adversary is successful in breaking the leakage resilience, meaning that if you want the adversary to be not successful, you have to satisfy this constraint. Okay, so the adversary will get the leakage from all of those files, and then he will try to recover the file. And the adversary that we built is very simple. Basically, we just picked the FIs to be uniformly random functions. Okay, and yeah, and then as I will show in a moment, the adversary will basically try to see whether this leakage vector that he sees uniquely defines the file, the secret that was secret shared. I'll explain in a second how this works. Okay, so to start out, just consider, so imagine we have a blue file and a green file, and there are different secrets, and we secret share them. So what is the probability that these specific two different secrets output the same leakage? Okay. Well, we know that because it's a secret sharing scheme, correctness has to hold. So any T players should be able to reconstruct the file. So that means that at least, and because the secrets are different, at least n minus T plus 1 shares are different. Okay? So this we get from the correctness. And because the leakage functions are random, that means that we will have n minus T plus 1 shares where we basically have a probability of 2 to the minus L of getting the same leakage. Okay? So this basically immediately gives us this probability. And then now we don't have two specific files. We say, what is the probability that any possible green file has the same leakage vector as the blue file? So we do a union bound. And we know that the capital T shares are enough to reconstruct the full vector of shares. And we know that every share has p bits. So we union bound over 2 to the p times t possible secret sharings over all possible secrets. So we get this bound for the probability that any other blue file has the same leakage as the green file. So that means we want to know what is the probability that this is not the case. And this not being the case is basically exactly the condition that our adversary would be successful, because if the green file is the only one that can have this specific leakage, then inefficiently we can just go over all secrets and check which of those files actually gives us this leakage, and then we can obtain the secret shared file. And so that if we want, then what we just do is, okay, let's say we want an adversary who succeeds with some constant probability, and if we kind of rewrite this inequality, we basically get this condition, and this condition tells us if this condition holds, the adversary is successful. So if we want the adversary to be not successful, then at the very least, this condition should not hold. So the lower bound is kind of very simple in the end.
So you could replace the F5 with the always independent or just random linear functions, right?
Yes. So the inefficiency doesn't come from the fact that they're like random organs.
The efficiency of the attack, just you said random F.
Oh, yeah.
But random linear function.
Sure. Yes. Yeah. So, so it would be a very interesting question whether we can do any such attack with an actual efficient adversary. So, given the leakage, can you efficiently somehow find which file was secret shared? Yes. Yeah. So that's all I have.
Thanks, Mark, both for the talk and for finishing, allowing us to get very so hopefully the next session the technical issues will be resolved. Any questions to Mark?
So what's the state of the app? What do you conjecture? I mean, just maybe can you summarize the gap between lower and upper bounds? And what
So the best upper bound for leakage-resilient secret sharing that we know is a paper I forgot the authors, but basically they get a share size which is 3 times that of Shamir secret sharing. So like the upper bound is very close to the best we can hope for. Like my personal guess is that the conjecture is true because like picking random functions seems, intuitively it seems like the best way for some.
With 1 bit leakage, sorry.
Yeah. So.
3 times share, 1 bit leakage, and orbit.
Oh, so the 3 times the share size tolerates even larger amounts of leakage. I think, a constant fraction of leakage actually, yes. And the share size is only 3 times that of Shamir secret sharing, so it's very efficient and has very good leakage. And so in terms of upper bound, we're very close. But again, kind of, even if you have enough shares to reconstruct a secret, there is still a lot of randomness left in the remaining shares, which makes sense because that's what the lower bound basically tells you. So to me, it seems that the conjecture that Yuval and the others posted in their paper should be true, because I would guess that in terms of generic attack, where you don't exploit some specific properties of the secret sharing scheme, this seems to be like an optimal attack. But I don't know how to prove their conjecture. Yeah.
So your intuition, I just want to see that I understood correctly, is that your attack is basically optimal, because your analysis was very loose. I was going to ask if you think it can be made tighter. And also maybe you could pick functions that are not generic, but like for any secret sharing scheme, I would pick some function that depends on the secret sharing scheme. I don't know.
Yeah, so I mean, at least in terms of like a generic attack, picking a random function, let's say with 1 bit leakage output, where you kind of like, you have a search space and every bit kind of cuts it in half, seems to be, very loosely speaking, kind of the optimal, asymptotically optimal way of going about it. But yeah, to show that Shamir's secret sharing is actually leakage resilient, like the conjecture is true, you would need to find some proper, so they show it over FP for some prime P. So you would need to find some specific algebraic hardness property, so to speak, to argue that the conjecture is true, and it seems hard to find such a algebraic property where you can argue that it's hard. So in their paper, they also show that if you do secret sharing over a field of small characteristic, then it's not leakage resilient because you have small additive subgroups. So if you want to argue that it is leakage resilient over FP, you would somehow need to argue that, for instance, you would need to argue that there are no small additive subgroups, and it's even hard to have any sort of approximate version of something like this, which like is completely unclear to me how you would go about this. Yeah.
Is there any hope to use the same lower bound you showed for other linear secret sharing schemes, CNF or something like that?
Maybe we didn't look at that yet. So I would have to look at the specific secret sharing scheme, but like we basically did the general lower bound, and we were interested in Shamir secret sharing, so we looked at that. Yeah.
Okay, thanks again, both to Andre and Mark. And,